All right, it's my great pleasure to introduce Josh Cantor, who's going to talk about how Cython works.
Thank you. So we'll see how this goes. So Cython, as all of you know, is it's an integral part of Sage. It's how we make everything fast that needs to be fast. And we have been modifying it, or by we I'm assuming Robert has been modifying it to add features that are necessary for development. I haven't actually done really any actual or any at all development, but I found Cython very interesting, and I had a couple of times tried to figure out how it worked quickly, and it didn't work quickly to figure out how it worked. And so over spring break, I spent some longer period of time trying to figure out how it works, and I think I more or less succeeded, but it's still pretty complicated. And so the goal of this is kind of to give a guide to how it works, so if someone wants to do some development, they maybe don't have the initial learning curve of figuring out how to analyze what the code is doing, because it's initially somewhat confusing. So basically, the goal of this is to explain what pieces of Cython do what and why it's designed the way it is. And also, I think it's it basically is, as I'll say, it is a compiler, and it's from some sense it's a very sophisticated piece of software. It's very interesting just as in and of itself. So the first thing I want to do is sort of indicate, so if I'm going to look at Cython, so if I unparse some version of Cython, I get this, and all of the source code is in sort of Cython, and there are, so the main...
Can you make that bigger?
I could.
Apple Plus, yeah.
Okay, so the two main, or the main directory is this compiler directory, as well as we'll see. And I'll at various points be pulling up various files in here to look at, but this is where most of the, in particular, main is where, when you actually call Cython, that's where it sort of starts running from, as you might guess. So the first thing to realize is Cython is a compiler. And actually, when I first started trying to figure out how Cython was working, I kind of got stuck on something, which I'll explain what it was later. And I ended up just sort of pulling, there's a standard compiler textbook, which has a big dragon on the cover that's sort of, and I read through the first couple of chapters of it, and then it made a lot more sense why it was, or what the design structure was. And so I'll kind of explain that design structure, but I would maybe recommend sort of looking over sort of something like that before you start, because you'll kind of understand why things are the way they are. So the first thing we have to think about is Cython is a compiler. How do we specify a programming language? That's the first thing. And basically, the standard way is through what's called a grammar. And sort of being very imprecise, a grammar basically is going to tell us how to decompose complex statements into simple ones. And just like, for example, if you have an English sentence and you know English grammar, I don't really know grammar very well, but if you did, you could sort of do some diagram, and you could sort of decompose this full sentence. I can write it as this phrase plus this, and this as a noun and a verb, and it tells you how to decompose complex things into simple ones. And basically, that's exactly what how you specify programming languages. In fact, there's a official Python grammar, which I guess maybe I won't pull it up. It's on the Python website. There's an official Python grammar, and here's some pieces of it. So for example, an identifier, so actually, when we look at the bottom first, so there's a regular expression notation is in here. So a plus means one or more of the thing before it, a star means 0 or more, the bar means an or, the bracket means 0 or 1 of the thing. So for example, an identifier, we can see it's either a letter or an underscore, followed by one or more letters, digits, or underscores. That tells us how to recognize what an identifier is going to be in Python. And an assignment statement is it's an equal sign. Assignment statement is it's a list of things you're assigned, or it's a target list and an equal sign plus some expression. And what is a target list? Well, it's a tuple or a list of targets. And so this tells you how to break some statement and sort of decompose it and sort of say which pieces of it correspond to which things within Python. This is the general idea. So basically, that's kind of that's kind of the thing. And so once we know how to do that, so that we'll come back to that later, how that kind of works. So the general structure, the way things work, is that we take our source code file, and there's going to be a lexical analyzer. And what is that going to do? Well, what it's going to do is it's going to just be reading through the file, and it's going to be trying to classify. I have a variable name or an identifier. I have a binary operator. I have a a function, whatever, and it's going to just sort of classify things into general categories of things and pass that off to something else, which is the parser, which is going to try and sort of use that to do the compilation process. But what the parser really wants to make is a parse tree. And I think I have a picture. So here's kind of the idea. So suppose I have, on the left is my code. So I have A equals 3, B equals 4, C equals 5. And then suppose I just want to parse that one last sentence. A equals B plus C. Well, what's going to happen is the lexical analyzer is going to go through and say, I have an A, that's an identifier. I have a binary operator, it's my assignment. I have another identifier, I have another binary operator, and I have another identifier. It's just going to send those things out. It's going to produce a stream of those things. And of course, you don't forget about what produced the token. You keep track of it, but you sort of, for the moment, you're sort of keeping track of exactly what produced it and what type of thing it is. And the thing you want to kind of produce is something on the right, where you have you can see that this statement, you can think of it as a tree. There's an equal sign, it has what's being assigned to and what's assigned, and then the thing that's assigned again can be decomposed into, this sort of tree structure is going to sort of spread out based on sort of how that, how things sort of propagate like that. Does that kind of make sense? So to emphasize, the tokens are these just sort of general classes of identifiers. They're going to be passed to the parser. You were going to say something?
I was just going to say, you can think of tokens as things delimited by white space.
Right.
So that way you don't have to break up an integer into its individual digits. It just says, here's a string of digits.
Right.
And
right. Yeah.
That's kind of a good way to envision the boundary.
Right. Yeah, exactly.
So the parser puts in the extra break. So if A equals B plus C, well, one string.
If you think about it with like a sentence, like if I was just giving you a list of words,
right.
the token just says, here's the list of words, and this word is a noun, and this is a verb, and this is a pronoun. And then the parser has to take this list of words plus these identifiers of what type of word they are and construct some meaningful thing out of it, basically.
Yeah. The tokenizer goes character by character and says, I have a, dot, dot, dot. Oh, look, I have a space. Space. I'm at the end of a token. Figure out what this token is and pass it off.
Right.
So.
And it might treat strings, for example, like within certain contexts, it might act differently,
yeah.
like within quotes or something, it might, so, right. Right, and yeah, so the tokens, basically, they're just sort of the individual words, but in addition to the word, you want to say what type of word is it? Is it a variable name, or is it an equal, or something that means there's slightly more data that you need. It's basically just like saying this is a noun, this is a verb, this is an adverb, this is a pronoun. That's kind of what it's basically doing as it's throwing it off to the parser.
Okay, so that happens before it even gets to the parser?
Yeah.
Mm-hmm.
Okay.
Yeah.
And all the stuff like string quoting happens in the tokenizer. So parser doesn't have to worry about, am I inside a string? You have a backslash in the quote. Is it a string that's quoted for single quotes? Do I ignore that?
Right. And
that's all happened before.
Yeah, that all happens in token. So, right, and as I said, this is kind of the graphical representation in the simple case of what we're trying to produce. And there's also a symbol table, which I'll say a little bit about. And basically what that is if I at some point in my code say that A equals 3, and later on I refer to A, well, how do I know what A was? And so basically when you initially create your variable A, there's some symbol table that's just going to be a way of organizing common data that is going to be necessary for the compilation process. And so there'll be, it's kind of, you might have at the first statement when A equals 3, you might have created an entry in the symbol table that said there's a variable called A and its value is 3. And then later on, when it hits that A, it can look up in the symbol table and say, oh, that's that variable that we said was 3 earlier on. And that's just something to do. Right. So the way I initially had been reading the Python code is I started at main and tried to trace the function calls. And if you do this, you end up being immediately going into this plex module, which I'll go back over here is this plex module. And the plex module seems extremely strange at first because it's kind of complicated and there's some weird sort of DFA stands for discrete finite automata. It's kind of, so let me explain what this thing is. So this is the lexical analyzer that actually does this process of saying whether something's an adverb or a noun in this analogy. And plex is a completely general lexical analyzer. It has nothing specific to Python really. And he specializes it for his use in Python, but plex is completely general. It has nothing specific to Python. And this is actually the part where the compiler textbook helped me figure out what was going on with this thing, because it's completely standard. Basically, it takes a list. Basically, as you saw earlier, I was able to sort of describe how to identify things in the language by regular expressions. And so basically what this does is it takes a list of regular expressions and produces an object that can tokenize strings and classify them according to the regular expressions you give it. And what's kind of interesting about it is, and I'm just going to, is the implementation, which is completely standard. If you look in any compiler book, it'll talk about this. It uses finite automata, and just to sort of give you an indication of why that is. So this is an automata that has 4 states, 1, 2, 3, 4, and I have transition maps which tell me how to go between states according to what symbol occurs in the stream. And so the idea is, if I have this regular expression, which is A or B repeated 1 or more times, and then ending with ABB, then I start, if there aren't, and you can see I'll just loop around. If there's 2 A's, I'll go from 1 to 1 twice. Of course, it has to end with ABB, so assuming it does, I'll sort of loop back and forth in the first state, and then eventually I'll end up at 4. And basically the way this automata works is it has some node, some tree with a bunch of nodes connected, and there's sort of ending nodes which tell you you match the regular expression, now sort of produce that into the stream. That's how it recognizes that you successfully matched something in the regular expression. And this is completely irrelevant to Python, but if you sort of trace through it and initially try and understand what is this scanner object that's doing the parsing, you're going to end up reading this and it's not completely clear why it's working the way it is. And so just trying to indicate so that you don't, so basically the point is that you don't really need to understand it unless you want to sort of see how you implement that. But the whole point is that this plex is a completely general lexical analyzer, and so now I'm going to start looking at so plex is totally general. So we need a scanner that's specific to Python, and that occurs in this guide. So compiler, so this is the object that, so this Pyrex scanner is the object that does the lexical analysis. And you can see it derives from scanner, which is in the plex module. And it just is what produces the stream of tokens. And so this lexicon, this describes the Python grammar, and you can see what he has is he has this makes lexicon produces the scanner object from this sequence of regular expressions. So just to go to the bottom here, you see he has a name regular expression, which over here a name is, well, as we said it was earlier, a name is a letter, or a letter is any of a letter or an underscore followed by letters or digits. That's exactly what we said earlier was how we were going to identify an identifier. And so his lexicon is going to, anytime it matches a name, is going to produce the token identifier. Anytime it matches an int constant, it's going to produce an int. And you can see that this just tells us, this is just exactly based on, it's going to tell us how to identify types of things that we see in our source code into classes of objects like this. So this is before any real understanding has done. We haven't said what the sentence means. That's really what the parser does. What?
Is it a joke? He has bra in quantum mechanics, and he leaves off the C.
I think, I don't know, just to be symmetric, I don't know. I think it's exactly from quantum mechanics. Yeah. Yeah. So this is, as I said, we haven't understood what our sentence means yet. All we have is classified it into pieces, and we're going to produce a stream of identifiers. So that's where we are now. So as I said, and let me say some more about it. So what are we trying to produce? So we've got our source code. We're producing this stream of tokens that's saying this is an identifier, this is an assignment operator, this is a binary operator. What are we going to turn that into that's going to help us compile this? So what we're going to do is we're going to create a parse tree. And as I said, a parse tree is just, you can just imagine that, like I said, the standard simple thing is to think A equals B should correspond to a tree where there's an equals and then an A and a B below it. And in general, you should be able to compile your code to some sort of tree-like structure that mirrors what it is. And that's what we want to do. So the thing to think about is how are we going to build up that tree? So we're going to build up our tree with nodes, and there's actually 2 files full of different types of nodes. So these are the nodes that the parser is going to put together. It's just going to literally just link them together with, each node has a reference to its subnodes, and link them together into some big structure that corresponds to the file that we inputted. And so this is kind of where, actually let me stop. Are there questions about sort of how things are going so far? Okay, so this is kind of where understanding Cython gets hard, because there's a lot of nodes, and there's a lot of different types of nodes, and there's a lot of code here. And sort of really understanding what's going on, so hopefully you'll get an abstract sense of kind of where things are happening, but really understanding exactly what's doing what is kind of difficult. Yeah?
Is the fact that it's all written in Python really helpful? As far as having written, do you know what I mean? Like if you had to write Cython in C.
The fact that you're compiling Python based on something that's written in Python?
Yeah, does it come up at all? Like a lot of constructions.
It really
in
doesn't.
Python,
I don't think other than
if you just sat down and written the whole thing in C.
Yeah, this structure is totally general. I mean, it would have been harder probably because but yeah, the fact that you're programming in Cython is completely not used. It's not used the fact that you're compiling a Python language in a Python compiler. That's really not. That has nothing to do with it. Strangely.
I don't think a val is used anywhere.
What?
I don't
No,
think
yeah,
val's
he never.
used.
Yeah, Python code is never actually evaluated. So.
Maybe to turn a string. No, I don't think it's that.
Yeah, I mean, he uses kind of functional type programming stuff a lot. So that would be, but that's really all he. I mean, it's really complete. There's nothing specific to Python. You could write it in anything.
Right.
Yeah.
Well, in theory, but
in theory, yeah.
In practice, you're saying you could too.
Yeah. It'd probably be easier to write it in Lisp than C, for example, or something. But based on kind of the way the code is structured, probably like Camel or something. Anyway, so so there's a basic node class, and it basically, you can see it's basically kind of a container object. So basically, if you pass it a dictionary, it'll just sort of add that stuff to its dictionary. So it's basically some pretty flimsy class without much stuff to it. And then there's a bunch of later nodes that are going to descend from it. And I'm going to come back and look at specific nodes later. The nodes.py file, these are kind of like, I would say, more higher level nodes. They're not really specific. And in contrast that to the other file of nodes is this expression nodes. And these are to some extent, I would say, as more atomic nodes. They're kind of lower level. So
yeah, I'd say the nodes are usually the statements.
Yeah.
You print something or do a loop, and the expr ones are like
strings
I'm an
and
addition,
floats.
or I'm a
I'm a long.
They have a value.
integer. Yeah, right. So that's kind of the way things are broken up. So right, and so going back, the nodes. So basically, the way this is going to work is once we've built up our tree, the nodes, they know what code they correspond to in Cython, and they kind of know. Basically, the idea is each node should know how to generate the code that corresponds to it. And so the way the compilation process is, once you've assembled this parse tree, you compile it by just propagating function calls down the parse tree. You tell every node to analyze what thing it's associated to and do some code analysis, and you tell every node to sort of do some other stage, and eventually every node should generate its C code. And that's basically the way the compilation process works. So it's really, I mean, it makes a lot of sense. You're basically saying each node understands what to do with its own little sort of function, and so that's how we're going to do the compilation process. And this is pretty standard, completely standard.
Yeah, like a good example is analyze types. And you say, well, what type are you? And like if it's an addition, it says, well, what type is my right hand, what type is my left hand? And use that to figure out what type I am. And just recurses like that.
Right. So you can kind of see that once we've constructed this tree, so this should give you a sense of kind of how it works. And now really the details of exactly how that happens are a little bit more difficult. So at least as far as the code generation. But and just as so this isn't even the full node. This is just defining what's in the node. So def node, this is a function definition. So like if you have def blah 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 in your Cython code, it gets a node, and of course, what does that node need to know? Well, it needs to know the name of the function, the arguments, if there's any sort of optional arguments, and also the doc string and the body of the function itself. So the function has there's a node object, and it has as a subnode the list of statements in the function. That's kind of makes sense. And here's a much more simpler node, a float node, which it knows that it's a double, and it can return its value. So it's kind of a little bit simpler. Right. So then, so we have this parser. Sorry, we have this lexical analyzer, which is going to produce this string of tokens, and we want to construct out of that this parse tree, which we're going to then use to generate our code. So the thing I haven't talked about yet is, well, I really haven't talked about how to generate the code, but the main thing I haven't talked about is how do we generate this parse tree. And I think this is kind of best done by, like, kind of everything here is just done by example, or sort of illustrated example, sort of, right, so the entry, and I'll show you maybe where the entry point occurs. It occurs in this main file, but the entry point is, right, so what is S? So S is this lexical analyzer. And s.sy is the current symbol in the stream of tokens. And you're basically going to repeatedly, these functions in this file are going to repeatedly tell S to give them the next token, and they're going to do something based on that. And I'll explain how that works. So P statement list, the way to think about this is your code is a list of statements. There's one sort of uber meta node, which is the list of statements associated to your file. Okay? And what's it going to, and so it's going to go through this, and it's going to repeatedly call this P statement function. So I've started in here. I know I'm at a, okay, so actually let me think about how to explain this a little bit. So what's going to happen is, as symbols come out of the stream of tokens, different functions in this file are going to be called. You're going to dispatch calls to different functions. And those functions are going to dispatch calls to other functions. And what they're going to do is, this process of sort of dispatching function is going to be used to build up the parse tree. So you're going to call different functions corresponding to what node you expect to make, and then it's going to do some analysis and actually produce that node object. So you start off with you can see that the thing that this is going to produce is it's going to produce a statement list node. So it's a node that has a list of statements in it. But in order to do that, it has to know what are the statements in it. So in order to do that, before it does this, it has a list of those statements, and it's going to call this P statement function. Let's look at that. I think it'll. So P statement. What does P statement do? Well, P statement just says, basically it's a big case switch. It looks at the symbol, and based on what's going on, it calls out to some other function. And based on, and that thing again looks at the stream of the symbol, and that calls to other functions. And eventually you sort of get down, you figured out what's going on, you produce a node and return it back upwards. And basically, this is why this is kind of hard to understand, because you can imagine that really thinking about tracing through, this is some very kind of complicated recursive sequence of calls that's going to depend on exactly what your source code is, but you can kind of see how by dispatching, for example, so if I have an if statement, I go to the P if statement, and then the if statement is going to analyze the block of code beneath the if, and it's going to sort of create the appropriate nodes for that, and that's going to call other functions, and that's going to build up this parse tree. I don't know does this make kind of sense the way I'm...
You kind of think of pointers moving through your file, and every time it's pointing to something.
Right. And
the parser says, what does it look like I'm pointing at? Oh, it looks like I'm pointing at a function. So I'm going to try to parse the function at this point. And then, inside there, as it's parsing the function, it's like, oh, it looks like I'm pointing to the first argument. I'm going to call the thing that parses the first argument. And when it's doing that, the first argument says, oh, it looks like I'm pointing to a type. And parses the type. Oh, it looks like I'm pointing to the name of the argument. And parses that. And it says, okay, I'm done parsing the argument. Drop down. Oh, now time to parse the next argument. So on.
Right. So this is kind of the way this works. So I mean, basically, if you sort of look through this, you can see for any, every for a P except clause. So if I find for P try statement, every sort of possible thing in the grammar has an associated function here, and the function here, P import, every possible sort of thing in the language has an associated function here, and that function is responsible for creating the node that is going to correspond to that line in the source code. It's basically what's going on. And so you start out with your list of nodes. For each node, you call this P statement. It does some analysis, and you're just going to go through, and you're going to end up with a node object, which is a list of statements. And each of those guys is going to have nodes that correspond to what type of statement they were, and it's sort of this big tree that goes down. Right. So, and so basically, in terms of if you wanted to actually modify Python, probably you would be likely to modify this file and nodes and expr nodes. That would be the most common. If you actually wanted to change the way Cython works, those are the files you would have to do something to, in most likelihood. Maybe something with the lexicon, potentially, if you really needed to change the way it was parsing stuff, but I don't think that's particularly. So this is kind of what I was just explaining about how this S is this scanner object, and we're these functions based on what's the next stream. S.cy is the current stream, token in the stream. We just repeatedly call the appropriate function to create the right node. And just as an example of something which Robert wrote, I think, so maybe he can say something about what was involved in doing it. So this plistmaker. So plistmaker, of course. So Robert added list comprehensions, right? So originally, I guess there was just a list maker, because you can imagine. So a list is your square brackets and there's stuff inside of it that's going to create a list. But so of course Robert added it so that this thing would be able to detect: are you actually making a list, or are you doing a regular expression, basically? So
a regular expression.
Right, for loop inside. And so so where is that?
For.
Yeah. So right. So right there you go. So. So he basically added it so inside of this thing, which could create a list, it could detect if you're doing a for loop, and if so. And Robert also added there's a list comprehension node. There's some nodes that correspond to list comprehensions that it creates the appropriate list comprehension node, and then that gets stuck in this parse tree, and so that when the compilation process happens, it just goes through and adds the right code. Of course, it's much more complicated than that, but I don't know if you have any things you can, words of wisdom. I guess we'll talk about this kind of later.
Yeah, I mean, that's the general idea. This was the first Cython hacking I ever really did. So.
Right. So this is so that you can see that basically this is what he. And I mean, one thing that's nice is everything is quite compartmentalized. I mean, to some extent. I mean, you really can just sort of think of adding a specific node of that corresponds to what you want to change. Maybe it's quite, the code is pretty well separated, so you can potentially change little things without massively destroying what it's worked with. Hopefully Robert will give us more insight into really how hard it was to do that. One problem about trying to explain the code generation process is that part actually, everything I've said so far you can understand abstractly. You don't really have to understand the Python C API. So I don't know if most of you are probably familiar, there's this Python C API which basically is how Python is implemented. And it's also how you write extension modules. You have to directly call the appropriate C functions. And there's the conventions on, there's some C structure that any Python object corresponds to a C structure of a particular type. And so how do you create a class? Well, you create and we'll see a little example of this, but how do you create a class? You have to create a particular C structure with a particular type and methods corresponding to some list of function pointers. And so to actually do that, to actually understand how the final code generation happens, you do have to understand the Python C API. And that's something which is not, that's a non-trivial step. It's not something which you can just abstractly know how that works. So
my first reaction to Cython was Pyrex at the time. I was like, well, hell with that. Why don't I just learn the Python C API and then I can write even faster code? And 1 month later, I was a very happy Cython.
Yeah, I mean, the Python.
Actually, yeah, 1 month later you went, oh, I need to write something to auto-generate this stupid C code. That's how I felt after learning the Python C API.
Yeah, it's non-trivial. So,
it's very error-prone.
Very error-prone. It's very, yeah. So, so one file I haven't mentioned, which is important, although I'm not going to say much. So I'm not going to say much about it, but actually I am. So as I mentioned, there's this symbol table object that I said was lived somewhere in the compilation process, and basically, as far as Cython goes, that's in the symtab.py file. And a symbol table, well, what is it? So we can have entries, and so here's an entry type. It can have lots of any entry can have lots of properties about, what is it? Is it a num value, or is it a C function, or stuff like that? And the actual symbol table is called a scope, and it's basically a collection of entries of different types. And the symbol table is important. For example, like if you have a list of variables, you know that they get maker. If you ever looked at the generated C code, and I'll do that in a moment, you'll see there's lots of things that are like, pix blah 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 101 something or other. So how does it know this is the 100th and one, double or something like this? So a lot of the name mingling that happens occurs in this symtab file. So that's basically. I mean, because it knows all of the doubles that are in the given scope, so it can figure out, it knows how to assign them numbers, and sort of it knows how to mingle them in the appropriate way.
It used to look up things too. When I have an A,
right.
I say, well, where is it? And it uses the symtable to say, oh, this is a local variable, or this is a module variable, or something.
Right. Yeah. So it's kind of this sort of repository of all the information, sort of keeps track of all the information of everything that's going on in a given sort of scope. Is basically what it's doing. And it can sort of, anytime you need to sort of have something like, something refer to something that happened before, or sort of figure out where is this statement? It's not, it doesn't live in the local scope, like a global variable. It can look it up and figure out what it is. And that's what that is. So, there's a lot of stuff in here, and again, I mean, there's lots of stuff in here. A lot of these functions are just so if I create declare a num or declare. A lot of the functions in here are for creating entries in the symbol table of a particular type. That's basically what kind of this was. And right, so as I mentioned, once you've constructed this parse tree, basically the way that the compilation process works is it goes through and it tells each node to do some analysis and eventually to generate the C code. And this actual process happens is, where it happens is in, maybe I'll just pull up the file. So there's this module node.py. So you can think about, I had nodes for individual statements in the file. There's actually a node that corresponds to the modules, sort of higher level nodes. And they're the ones that, so this process implementation is where the compilation really starts, really happens. And this on thing, that is one of these symbol table scopes that's going to be passed into the all of the functions. So just to sort of see what's kind of going on, so let me open up. Let's sort of just kind of scan through some examples. So we see that the first thing it does is it calls analyze declarations. So let's just look at some examples of those types of functions. So that'll be in, for example, nodes. Right. So analyze declarations. So I mean, this is only going to give you a feel for kind of what's happening. I'm going to show a simpler example. The analyze declaration, I mean, basically it's just going through and, I mean, do you have any simple way of describing?
Well, I mean, here in the nodes, it's just going to recursively call all the way down. And then if you have an assignment, like A equals 3, analyze declarations will say, oh, I have a variable called A. So I want to put that variable into my scope.
So that's why this on, which is the scope, it's passed, basically the node recursively calls and it passes the scope along. And once it gets to the bottom, as you said, it has the scope that was passed all the way from the top, and it can add stuff to the scope. And that's kind of right. So, and then sort of, right, so then once this has happened, you've added all the, for example, all the C classes that you're going to add have already been put into the on, because you've put them in the symbol table, and so it can now check them, do some analysis. And then body is going to be the body of the code, and it's going to go and call this, it's going to recursively call all the analyze. So basically what this, anytime any of these self.analyze is going to recursively call every analyze declarations function in every node all the way to the bottom of the source code. And self.analyze expressions is going to recursively call every analyze expressions all the way to the bottom. And that's basically what's going to happen on all of these functions. And eventually you're going to get to generate C code. It's going to recursively call everyone's generate C code all the way to the bottom. And so you can imagine that really, I mean, that's what's going on. Really understanding exactly what that means is non-trivial, especially because generate C code, that's really involves the Python C API. But this is the way in which it's implemented. And so that's pretty cool, I think. Right, so, yeah, so are there any questions about this? First of all, any questions or any comments from Robert about kind of?
So one thing is there's this phase shift. For instance, if you're inside a function, you declare a variable. That actually doesn't happen in this top analyze declarations. Because in the top analyze declarations, what it does is it says, oh, I have a function named foo. And that's the only thing that it gets declared. And then actually later on, when you actually go to generate the function, then the function foo says, oh, I need to analyze declarations inside of myself.
Right.
So you have to be aware that there's this kind of like phase shift going on, where bodies of things aren't necessarily analyzed at the same time as their scope.
Right. Another way to think about this is I said that my Python, my source code was a list of statements, but then I have a function, and the function itself has a list of statements. And the if statement inside of the function has a list of statements, and so the analyze declaration might only call, it might not actually call up to the analyze declarations inside of the sort of a function object. So there's really lists of sort of, you can think about this, you have lists of statements, but you might have individual objects themselves have their own lists of statements that might not get evaluated or might not get processed at the same time as the outer scope. That's what's going on. And there are scope, there's a scope object for the whole module with the symbol table, and then the function itself will have its own scope inside of the function. That's how it'll know about local variables and stuff like this. And so that's kind of the flavor of how things work. And you can, I mean, you have to just look at things and sort of try and figure out how they're working. It's kind of probably better to try and figure out how a specific thing works as opposed to how everything works, because there's kind of too much stuff to really, I don't know. Right, and so specifically what code gets generated, that involves, that's kind of the stage of going from, your parse tree to writing your assembly if you're writing a compiler for C. So that part you kind of have to know what's going on for that, and I don't really, even if I did, I couldn't, and I don't, so I'm not going to talk about that. But there are a few features of the generated C code that I do want to talk about, which are kind of understandable in general. So let me pull up.
Wait,
yeah.
If you pause for a second, and so the Python interpreter takes as input kind of nearly the same thing, and does many of the same things, and at some point does very different things.
Right.
Like any, overarching. I mean, it's
sort of
almost the same language, but there's a compiler and an interpreter. And
so
I wonder what the relation is between the two.
I would think that the relationship would be up until the process implementation part. Well, actually, even further than that, actually. So probably, let me pull up the previous file. So up until the generate C code, everything up to here, you could probably write a Python compiler duplicating this exact structure, and the only thing that you would have to change would be the last.
When you just said Python compiler.
Python interpreter.
That's what you meant to say. Okay, just making sure.
Right. Up until the last 3 lines, everything could probably work the same. And the only difference is you would then have to generate code for your virtual machine or whatever instead of for your Python C API.
So yeah, one thing that's missing in Python that makes things a lot easier is you don't have types. And so there's no type analysis that ever has to happen because everything's an object.
Right.
And so everything you call is an object, you always get an object back. You can always do everything you can do with anything with an object. So that makes a huge number of things a lot easier.
Right.
And there's a lot less declaration that has to go on because you don't have to declare types. And then the other thing is, so Python actually compiles into a Python bytecode.
Right.
And which there's a lot of correspondence between Python bytecode and the actual C API.
Right. So yeah, I guess to some extent, this is more than you would need to compile Python because it interpret Python because there's more sort of, this language it's not quite a superset because there's some things that we don't support that you can do, but it's almost a superset. So that
right.
And C is very rigid about you have to declare things before you use them. You have to declare all these structs ahead of time before you use them, which is Python. Everything's a dictionary, you're running some code and you can just stick something extra into the dictionary and it just works.
Right.
If it was C, you'd have to know about that way ahead of time to say, I need a slot for this, that I'm going to run into 100 lines down. Yeah.
So it's much more difficult to compile Python than to interpret Python.
Yes.
Yes.
I read an interesting article by one of the authors of Ruby recently where he says the easier a language is to use, the harder it is to interpret or compile.
that would make a lot of sense.
Yeah.
That's why Lisp is so easy.
Easy to compile or to compile.
What did you say?
Which is why Lisp is so easy to interpret.
Oh. So this part might not make any sense, and if so, I apologize. So here's a very simple, on the left Python file, it's just a cdef class that has a double, that contains a double, and it has a cdef method that just does something stupid with the list comprehension. And those 4 or 5 lines, 6 lines, compile it to this incredibly long 700 line C file. So
should be noted that there's a constant overhead of about, I don't know, 500 lines.
yeah, so right, so the first, you can kind of see everything, the first couple 100, 200, 300 lines are sort of stuff that's, well, I guess up until about here, is stuff that's in every single, I guess it's not, I guess it's about 12
There's a
hours
bunch
a
of
year.
stuff at the bottom too.
Yeah, so there's a lot of stuff that's just everywhere. But, you know, for example, all these declarations of what these things are, that's just in everything. So,
how generic is that? Should it be separated out into another file and included? Or is it really specialized?
No, it's actually very generic. It's a question of, I've thought about doing that.
They make it more readable and stuff if it were in a separate file.
Yeah.
But
Save phase 2 probably.
yeah, because we'll just put it in user local.
You can make macros out of those, the header and footer.
I think the point is that they wanted to output a single C file that you just have to
Yeah.
not to worry about
includes and stuff.
includes and all that.
So, so the actual object, C object that corresponds to your example class is this structure right here. And you can see what this structure is. This is kind of this name lane. There's a special structure just for this object, just for this type. And so every Python object has this PyObject head. This is a macro that expands to a list of some stuff that every Python object has to have. And in addition to those things, our Python object has this struct, which I'll say a little bit more. So one thing you might be wondering is how is the CDEF, one thing that's very different that you can do in Python that you can't do in Python is the CDEF methods. How is that implemented? And so that's what this object, this vtab, which is a abbreviation for virtual vtable, which if you know C++, there's a virtual function table, and it's basically implemented exactly the same. What it is it's a list of function pointers, more or less, and your CDEF methods you get pointers to them put in that, and that's basically how it's implemented. And when you call those functions, you're just dereferencing that pointer and calling that function from that function pointer.
And that's how you can override it.
And that, yeah, because you just change what the pointer is assigned to.
A vtab struct is just like a function pointer?
It's
a list of function
list
pointers.
Of function pointers. It's an array of function. It's this thing which has too many stars for me to really parse. It should be an array of function pointers. And also you can see that any CDEF object that you have will be, instead of being part of the Python dictionary, it'll just be stuck directly in the class, as you would expect. So the double is just sitting right there.
With no mangling.
Right. Right. And yeah, so that's one thing to be aware of. Gary Furnish is sometimes concerned about the virtual. He was concerned about the virtual function table, the overheaded. I don't know what his position on that is. But that's how it's implemented. And right, so yeah, and so I mean you can see it's kind of really hard to really see exactly what corresponds to what, but there are some I wanted to find. So let me find this example method. I forgot what class it is. Yeah, so this function corresponds to this example method on the left, and you can see there's a lot of stuff going on here. Basically, yeah, I guess I don't. It's kind of hard to say anything specific about it, but you can kind of. An interesting exercise is to try and look at. You know that this thing corresponds to that key list maker thing I showed you, and you might try and sort of pick out those nodes that it creates, and you might try and think if you can kind of see how does the node objects, and when they do their analysis and do their code generation, why is it that this particular chunk of code gets produced? That would kind of be a good exercise. I don't know if you
might want to start with something simple, because there's a Python function call and an iterator, and
yeah.
Making a list and an assignment and all.
Yeah.
Right in that same node. So.
Yeah. Okay. So maybe start with 2 + 2.
Yeah.
It's the unlikely. That's everywhere.
Oh, so
Unlikely, not this random variable with no significant name. Like I see that everywhere.
So there's this, there's a GCC pragma that can tell the compiler that to give hints about branch prediction that this branch is probably not going to be taken. And the unlikely is everywhere because everything could possibly throw an error, but it probably won't.
Okay.
So you have to make sure that everything didn't throw an error, but you don't want it to be,
Okay.
you don't want to keep flushing your cache every
So
time.
the unlikely function is just something that, in most cases, does very little work and returns false.
So basically, you can just remove it, right? I mean,
It's just a macro that says if you're able to give branch prediction hints, hint that this branch is not going to be taken.
so like
But it
this
does issue a
statement,
function.
this statement here, like if not unlikely not, sorry, if unlikely not picks one, is really saying if not picks one, and also telling the compiler that it's unlikely that this will be not. Isn't that basically it?
Mm-hmm.
Oh,
Yeah.
so unlikely is actually a compiler command.
It
It's a
actually
compiler,
like
yeah.
goes into the GCC compiler and loads different instructions into the command chain,
I
so
see.
that when it's pipelined, you don't have to stall the pipeline cache
Right, right.
while it runs those.
Yeah, so you can kind of imagine those are just not there, and all it's telling it is what to do with, in that case, or sort of how to kind of try to implement that. And yeah, so
Sorry, is that something you added, or was it in Pyrex originally?
No, that was something I added.
And does it actually help?
In some cases, it doesn't help as much as I was hoping. So, I mean, because I guess what happens is the compiler, if it doesn't have any hints, it does a pretty good job of guessing it.
Ah, okay, right.
So,
Can you call that, or can you give it hints from within Python? Or only you do that?
I think it's usually best to let the compiler do things. Like, I mean, these are things where clearly, you know, you have to make sure that you catch an error, otherwise it'll segfault because, you know, you have some null value that's supposed to be a Python object. But it's very, very unlikely to actually be in it. And so I think it has more of a place in auto-generated code than, I mean, you could like try to double guess the compiler, but usually when people double guess the compiler's right. In my experience. So, but you can, you know, create a CDEF, CDEF extern from star, you know, bint unlikely bint.
So like here this fails exactly when you run out of RAM. I mean, is that the only imaginable situation where that would fail in this particular case? I mean, making a list with...
Yeah, like I can't imagine any other reason. I mean, why would range fail? It shouldn't unless you run out of RAM. So,
Pass it card.
Well, here it gets 0.
Oh, it gets
Gets the int constant 0.
I guess one thing to point out, which is that your initial L is this pick the L guy, and all of this stuff in here occurs with other variables, and it's not until the very end that you actually end up assigning to the original guy. So that's something which happens if sometimes you're trying to follow through. Is that we use temporary variables for a lot of the stuff, and it won't actually end up giving the thing you think you're assigning to won't happen until like 30 lines later than it seems like it should. So.
And
Is that just the way Python language works? Like
Yeah,
make
because
this
if-
list and it's just its own thing and then assign it over to this other.
if an error happened in that loop and you were to catch it, the L would be unmodified. It's only after the list is successfully created would actually
Right.
assign the curse.
Yeah. So that's basic. So this is more or less how Cython is implemented, and it's kind of hopefully if you wanted to now go look at the Cython source code, you could maybe have a better chance of, or maybe the learning curve will be hopefully made not as steep as I thought it was when I first tried to sort of try and figure out what was going on.
Why do you do the checking whether it's a list or not within the for loop rather than the other way around?
That's so that you don't duplicate the code of the for loop.
Right, but is that, it just turns out that that one if isn't very expensive compared to the other overhead.
Well, to get away with not having that if, you'd have to make 2 loops.
Yeah, I know. But actually I thought you did. So it just turns out making 2 loops is
Well,
too
the loop could be
expensive.
arbitrarily big.
Right. Okay.
So
But I mean, it's sort of a trade-off. You could do that,
you
and you don't, and it would be more complicated to write
But
actually. Would
yeah.
be way more
Pilot-
complicated to write.
Pilot's check exact actually the pointer compare.
Ah.
And on top of that, if it's a small loop,
Uh-huh.
hopefully your processor does branch prediction and remembers what it did last time.
I see. Ah, that's pretty cool.
So I don't know if there's much.
Yeah,
I mean,
because it's exactly the same check every time.
you're not going to gain much on a small thing, and you're not going to gain much on a large thing. I mean, you're going to lose a lot if you would duplicate the large thing. So.
That's true. That was just like one little optimization Robert added, which massively speeds up Python over Pyrex in some cases.
So what about all these PyIncref pynums?
Yeah. If none went away, you would be in bad shape.
None can go away.
If you decref it,
Because
because decref
it
supposed to
gets
be
garbage
fast.
collected,
Oh,
it can go away.
Because the decref doesn't have special code to say if this is none, don't bother, because that would slow down everything else for you.
Yeah.
Right,
Yeah.
okay.
Wait, what were you looking at?
Is this
Why bother reference counting none?
You reference count none,
Oh,
like a
yeah.
ridiculous amount.
Yeah.
We don't
Well,
want.
Yeah. Because the thing is, one of the reasons you do this is because you need to put something in it. So when you assign to it, you have to decref the things that's there. And so if nothing's there to begin with, you have to put something there that's allowable to be decrefed
Okay.
when on an assignment.
Okay.
So there is some talk about getting rid of this because you could set it to null and then because in Python it'll throw a local variable error if you try to use a variable that's not assigned yet. But that involves a lot more control flow analysis than you can do.
So I don't really have anything. I don't know, I'm sure Robert will say much more useful things next week when he talks, and hopefully we'll.
I have a much better feeling why yield isn't implemented in Python.
I see.
After looking at all this, 'cause it's like,
Why isn't yield?
maybe Gary Furnish can do that.
Well, the interesting thing about yield is yield makes a def statement into a completely different thing.
Mhm.
Like it's no longer a function; it's a function that returns a function.
Right.
So you have to, somehow you go down this tree and then suddenly you change your mind about it.
Yeah, and then you have to, so you have to like detect whether or not you have a yield, and if you do have a yield, then
But it's completely different than,
yeah. And then you have to be able to like jump into an arbitrary position in your code, return from there, and then jump back next time. Next is called.
in other words, you can totally do it.
Yeah. I mean, I almost implemented it.
Yeah.
And then I kind of saw a bigger picture.
Is this almost like you had it almost coded up and there was
No,
one
you're-
point you just,
It was mostly coded up, but then I saw that it would be better to do generic closures. So like def statements inside def statements. There's a lot of similarity there.
right.
Yeah, that would be nice.
That, that hasn't been done yet, right? Has anyone?
So what's the
been
list
trying
of
to do
things that need to be done?
Yes, yeah, I give it, yeah.
Okay, so like, so for Python compatibility, def statement, like inner nested def statements and nested classes are not yet implemented. The yield statement is not yet implemented. You can't do import, from blah import star, and I think that's about it for compatibility with normal Python. Oh, and decorators.
Decorators, yeah.
Decorators will be really easy.
Yeah, decorators are straightforward.
So. Yeah, and then there's some Python 3000 compatibility stuff.
Wouldn't decorators be like 3 parsing or something?
Yeah, so there's actually a lot of talk about transformations. This is one of DAG's big things. Instead of modifying the parser a lot, the thing is you can just modify the parse tree instead of having to write new functionality into the code base itself. And so, for instance, decorators can be implemented as modifying a parse tree. So, yeah.
So that's all I have, and hopefully there'll be a part 2 to this, which will tell you how to actually hack Python.